Okay. That's wonderful. Okay, ladies and gentlemen. Guys. Hey. Okay. So you just finished what's possibly the most difficult part of electromagnetism, and that is dealing with all the crazy formulas in electrostatics. Well, we still have to use a few of them. So today, we're going to talk about, rather than what happens when charges are held in place, what happens when charges move. Now, first and foremost, let's refire some neurons. What do charges create when they're held in place? They do create a potential, but what, in general, around the charge do they create? A gravitational or a field, right? So a positive charge held in place creates a field emanating outward. And in what direction do we draw that field? Out. Okay, so we draw an outward field like so. And a negative charge has what kind of field? An inward field. So we're going to continue with the analogy that when you put an object on the planet, like, when you hold an object on the planet and you drop it, that object has a certain potential energy, and it loses potential energy when you drop it. So my ball has potential energy. More up here, less down here. And the difference in potential energy is work. And if I basically say this is 0, I can put a little spider right there and do work on the spider. Okay? Because something that has mass is attracted to something else that has mass, like the Earth. Okay? Now, electrostatics works pretty much the same way. Something that has a charge is attracted to something else that has a charge when you place it in its field. So if my baseball is a positive charge, it produces a positive field emanating outward. And my glow ball is a negative charge. What does a negative charge do? Yeah, it feels a force of attraction towards the positive field, or positive charge. So the positive charge creates a field outward. If I put a negative charge in that field, there's a force given to us by Coulomb's law. Remember Coulomb? That K, Q, Q over D, D? Remember that? K, Q1, Q2 over D squared? So we have the Coulomb's law, and Coulomb's law produces a force on the charged body, and that is pulled inward with an acceleration if it has any kind of mass. If it doesn't have any kind of mass, or regardless of whether it has mass, it has a potential energy. So just like you and I have a potential energy when we are composed of a mass in a gravitational field, a height above that field, a charged body has electrical potential energy when it has charge in an electric field a distance d from the field. So with a gravitational thing, we have a big M, and you have a ball that has M and distance h above, and it also has, or it's in the gravitational field, how do I show this? G, then it has a potential energy equal to mgh. Similarly, if we get an electric field, this is an electric field, and you put a positive charge or a negative charge above it, it has a charge q, a distance d away, and it's feeling a field E. Its potential energy is the same thing. Instead of M, we use Q. Instead of G, we use E. And instead of H, we use D. QBD. Yeah?
Why is
convention. So we don't have negative energy from electrons. Because the electron would have a negative Q. It doesn't need to be there. It's just a lot of times you see it there. But yeah, it's just convention. Okay. Does this idea make sense so far? All right, so let's move on. Okay, so potential difference is the difference from where you are to where you're going. Like if you jump off a cliff into a lake, there's a difference between the height of the cliff and where the water you're going to hit. If that difference was not there, then you wouldn't make much of a splash. There would be no reason for you to go anywhere. There would be no place to go. Potential difference is the charge's place to go. It's the reason for them to go. They want to flow from an area of high potential to an area of low potential. And just like we learned last time, when you take the potential energy and you divide by charge, you get the potential difference, which is formulas for it in a second. So again, potential energy with gravity is mgh. If you divide out the m from the mgh, you get gh. With electrostatics, potential energy is QED. You divide out Q and you get ED, and then you get the formulas, which we're going to talk about here in a second. These. V equals ED. So you've actually seen this formula. This is what happens when you take this formula and allow it to proceed out, the QED. You take the QED divided by Q and you get E. In other words, the voltage or the potential difference a charge will feel is simply the strength of the field divided by where you are in the field. So you might think of the potential that this charge feels as it goes from position 1 to position 2. Its potential would simply be the strength of the field multiplied by how big that difference is in real space. That's potential. Yeah, it's kind of esoteric until you mess around with it. Now, if you remember last time, we used Coulomb's law, and we found out how to determine the strength of an electric field based on a single charged particle, and that was KQ over d squared. So a charge Q produces a field strength E when we look at where our test charge is, where in the field we care about, multiplied by Coulomb's constant. Well, if you take this formula and you multiply it by D, take E, multiply it by D again, you get V equals KQ over only 1D. Okay. That is the potential of any location in the field. This is field strength. This is the potential of any location in that field. It's going to get better, I promise. I didn't understand it all in my first go through, or my second, or third, or fourth, or fifth. It took me a lot of time to figure this out too. I still don't have it all together. But what we're talking about next is going to be a lot of fun. I just want to make sure we all got this, and we all know this before we move on. That you need a potential. The takeaway from this is you need a potential for charges to flow. If there is no potential, charges will not flow. Hello. Awesome. Thanks. So you need a potential for charges to flow. Because this is physics and not chemistry, I'm not going to go into a lot of detail about what creates the potential, chemical reactions, differences in metal. If you're into chemistry, we can talk about it next year or after school sometime. But differences in metal create potential, chemistry, chemical reactions create potential. But this battery is rated at 1.5 volts. So we can arbitrarily say the bottom of the battery is 0 and the top of the battery is 1.5. We'll make the positive side 1.5 and the bottom 0, so we'll have a potential of 1.5 volts. Maybe it's -5 and +1. Maybe it's -1 and +5. Maybe it's +5 and +3.5. But there's a difference between the high potential and low potential of 1.5 volts. Capiche? All right. Moving on. Capacitors. Capacitors are awesome. Capacitors are like camp counselors. Remember summer camp? Maybe you still go to summer camp. Remember how there was the girls' cabin and the guys' cabin? And you got in trouble if guys ended up in the girls' cabin and girls ended up in the guys' cabin? And to keep that from happening, there was camp counselors in the middle. They put the camp counselors in the middle so they could be like out there with their telescopes and binoculars and shotguns and like, get back into your hole. But yeah, so that's how capacitors work. What capacitors do is they take charges where the positives and negatives are all intermingled and they tear them apart. And they put the and they put the positives over here and the negatives over here. And right in the middle, they put the camp counselors. Only the camp counselors have a special name. They're called dielectrics. The dielectric is a special material that doesn't allow charge to flow through, at least not easily. So a capacitor works like this. You have two conductors separated by a dielectric. 3 pieces are required. You apply a potential difference and tear the charges apart. Put positives on one side, put negatives on the other, and stick the dielectric in between. So the charges can't come back. They used to have these crazy disposable cameras. Luckily, a former student of mine worked at someplace, and he was able to give me a whole bunch of them. Yeah. Yes. So the camp counselor part, or what's actually going on?
What was going on? 3 parts.
3 parts. Conductor, conductor, in the middle, insulator. The insulator is called a dielectric. And what happens is you apply a potential and pull the charges apart. So you apply a potential, go to bed, positives over there, negatives over there, and the charges separate. Now, if given the chance, those charges would love to neutralize again because opposites attract, right? The negatives are attracted to the positives. They want to get back together. But we put something in the middle to keep that from happening. That allows us to store a lot of charge. That's what happens in a camera flash. These old 35mm camera had a capacitor. There's a capacitor. In fact, there's a few of them on your desk, and I hope, uh-oh, I lost my awesome one. Here it is. Okay, so I don't know where the capacitors are, just hand out, let's look like 1 per row. These are capacitors. I discharged them because we're about frying each other. You think of a surgeon. But, so this is what happens. You apply a potential difference using a battery. Here we go. Using a battery, and that charges the capacitor. Charge separates. And if you allow the charges to move back together, that's what they do. They jump back and forth. They jump as fast as they can. They frequently create a spark. I'm doing it over here. So all that's powering this capacitor is a tiny little 1.5 volt battery. Now, no one's afraid of touching at the ends of a 1.5 volt battery. However, don't recommend touching the poles of capacitor. This is a tiny capacitor. We're talking about micro units of capacitance, not a lot. Charge it up and discharge. You will? Cool. Okay, let me tell you what's going to happen if you touch it. I actually got a teacher 10 years ago to touch it. He didn't know what it was. And he's like, there was profanity. So let me tell you what's going on. When I bring the screwdriver to the poles of the capacitor, I now give the capacitor's charges somewhere to go. I allow the negatives to go over, or the positives. I basically allow them to neutralize, the charges to move. And what you're seeing is superheated metal. That sparks are superheated metal because electricity is traveling so fast, the metal is torn away from its neighboring atoms. Yeah.
So if you were to touch it, you'd be like a screwdriver kind of?
Mm-hmm. Only there wouldn't be any sparks. Instead, there would be tiny boiled cells. There'd be a little black mark where the electricity went in and boiled the water in your cells really fast. Yeah. Because you can if you want. It'll hurt, but only for a little while. And what are you hearing, by the way, when you see that spark? What are you hearing?
Yeah.
A snap. What's a snap? It's 2 words. It's SB.
I guess it's not so much about
You're breaking the sound barrier. The air is becoming superheated and going boom, and those little pieces of sparks are going really fast, and you're hearing a tiny little shock, a tiny little sonic boom. Okay, I'm going to leave these charged up so anybody who's stupid enough to pick them up. What is this? Okay, so that's how a capacitor works. So A potential difference is applied to the capacitor. Charges build up on either side of the capacitor, and they stay that way, ideally, because the dielectric keeps the charges from going back. And we allow it to store and store and store and store. That's why a tiny little 1.5 volt battery, no one's ever like, don't touch the ends, because it's only a 1.5 volt battery. But that 1.5 volt battery is storing a whole bunch of charge to be let out that fast. My camera's still recording? Sometimes when there's, good, okay, sometimes when there's sparks, electricity goes all weird. Little electromagnetic interference going on, we'll talk about that. We'll talk about that in EMI in June. Okay, so that's a capacitor. So you can imagine a capacitor, it's basically two plates that are overlapping each other. So if you look on it on an end like this, and I apply to it a potential difference. I'll tell you what that means next unit. And when I apply that potential difference, the charge is separated. A bunch of negatives on this side and a bunch of positives on this side. What I want you to think about is, what does the electric field look like inside there? And in between is the dielectric to keep the charges from going back. So we take away the voltage source. I'm going to take away the voltage source. See the light still on? The capacitor is still charged. The voltage source is removed. Put the voltage source back in, and I can recharge the capacitor. Take away the voltage source. It doesn't need to be there. The charges are already separated. Oh, this one never charged. How embarrassing. You must be so embarrassed. So, there we go. So the voltage source is gone, but the charges are now separated in the capacitor, and I can discharge the capacitor. Yeah, even though I know it's coming, it still bothers me too. Little shock wave. Okay. So if we were to draw the electric field inside the capacitor, what would it look like? If we were to draw the electric field inside the capacitor, what would it look like? Take 5 seconds and convince your neighbor what the direction those arrows go. Okay. Show me with your fingers what direction the arrows go. Good. Yep, they go like this. They go that way. Because you have a positive field from the positives here. And remember, negatives go towards, so negatives go towards, and positives go away, so the field will look like this. And then there's these other things called edge conditions or boundary conditions. Because the positives go in every direction, there are positives here that are going to go like this. They get kind of fat in the end. Yeah, that's an electric field inside. Another thing that's really cool, and it's not necessary for this level of physics, but it will be for next year. Everywhere inside the capacitor, the electric field magnitude is the same. It's the same everywhere inside. Because here, you get a big field from the positive and a little from the negative. Here, you get a big field from the negative and a little from the positive. Here, it's the same positive and negative. And those two things sum out. So everywhere inside the capacitor, the electric field strength is the same. It's kind of a neat idea, because you get a little bit of positive, or you get a lot of positive, a little negative, a lot of negative, a little positive, equal positive, negative, everywhere in the same. Those two fields will add up together, so the electric field inside the capacitor is the same everywhere. Okay, questions about a capacitor? Yes. Edge conditions. Yeah, edge conditions or boundary conditions. And I've only seen that ever tested at the AP level. But if you take AP Physics 2 next year, you want to know about, that does happen, because the positives go out in every direction, they curve. Okay, trivia. Don't need to write anything on here. I do have to turn off the video, because otherwise Google will kick the video out if I try to upload it. It's a great video. Okay, so capacitance has some formulas. I don't really like how I wrote and how it is usually written for capacitance. Capacitance is usually written as the quotient of charge over potential. I think it's easier to think of capacitance as Q equals CV. In other words, how much charge you can actually store is a product of how big your capacitor is and what potential you apply to it. I think it's just easier to see it that way. It's Q equals CV rather than C equals Q over V. So I like to think of it as the bigger your capacitor and the more potential you apply to it, the more charge you can store. And remember, when we're talking about charge being stored, we're not necessarily talking about adding charges, we're talking about separating them. Now, I want to show you what the capacitor looks like. So you have the little cylinders around here. This is what the capacitor looks like. This is one of those photocapacitors that I gave you where I took the cover off. It's basically an insulator, in this case paper, the dielectric, then one piece of metal, the conductor, then another piece of paper, the dielectric, another piece of metal. And it's all rolled up like a cinnamon roll. So you basically go layer, 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 and you roll it all up. Now, when you're trying to make good capacitors, and having small capacitors is very, very, very important. You want to make a lot of money, then develop really good capacitors and sell your design to Tesla or Samsung or LG, because they need tiny capacitors to make your phone smaller or to store more energy in an electric car. And the way you make capacitors bigger, stronger, is make their area larger. So the larger the area, and it should make sense, the larger the area, the bigger the capacitor. Or you can come up with a better dielectric. The epsilon here, that is a little epsilon, the epsilon here is a representation of the strength of the dielectric. That's called the vacuum permittivity of space. That's the dielectric when all you have is air. Metal, air, metal. Most dielectrics are vastly superior to that, but that's the formula. Epsilon naught is the dielectric for air. You might have like epsilon plastic. Dielectric, you just use plastic. Okay. So the better your dielectric, the higher your capacitance will be, the more charge you can store. Also, the closer you can get the plates together, the more charge you can store. So if you make the plates very, very close together, when D becomes very small, C does what? If a denominator gets smaller, the number gets bigger. So you want to get the plates as small as possible, as close as possible. Unfortunately, there's a point at which when your D is too small, you can't store any more charge because you'll overwhelm the dielectric. So the idea is when you want to make, you got to be careful with the small d because you might overwhelm your dielectric and your capacitor will just fail. So there's a dance between the strength of your dielectric and how close you can get the plates together. The closer you can get the plates, the stronger your dielectric, the better your capacitor will be, and the smaller your capacitor has to be of a certain capacitance. Yeah.
Okay, so the hobbyist dude, the Michael
Faraday, yeah.
Faraday, is that Faraday Futures? Like, is that anything?
Named after him.
Okay.
Yeah. Just like Tesla was named after Nikola Tesla, Faraday Future, if you can call it a company, was named after Faraday. Yeah, so Faraday was a crazy guy. He wrote a bunch of crazy stuff. I have one of his books. It's A Chemical History of a Candle. It's a book that thick on a candle. Give you an idea about what Faraday was. I'll get that in a second. So the variable for capacitance is C. The unit for capacitance is the farad. The farad. And a farad is an enormous amount of capacitance because a farad is the amount of capacitance you would need to use to hold 1 coulomb at 1 volt. And a coulomb's a pretty large amount. So a 1 farad capacitor would be about this big. This going through your chest would kill you. Easy. Okay, question. A Faraday cage is a wire mesh that is grounded so the electric fields can't penetrate. So if you were in a Faraday cage, you could technically walk into an electric storm and all the electricity would go around you. And the same thing happens for electromagnetic waves. So if you put your phone into a Faraday cage, you won't get any more signal because what will happen is the waves will strike the cage and basically become excited electrons in the cage itself. So that's what I want to do. I want to build a big Faraday cage and then put it in every classroom. So when somebody confiscates your phone, we just slide it in. It's like, everybody put your phone in the Faraday cage and slide it in. That way everyone's phones will just get no signal and they won't buzz and beep anymore. One of these days. Anyway, so the amount of energy you can store in a capacitor is a function of the capacitance itself and the potential you apply to it. Now this capacitor, you're going to need a calculator if you don't already have one. This capacitor is rated, it's written on here, it's rated at 100 microfarads. 100 times 10 to the negative 6 farads. It's also rated at 330 volts. And the amount of energy in a capacitor is given to us as 1/2 CV squared. So how much energy can this capacitor hold? This is actually bigger. If you're wondering how much a joule is, this is kind of fun. Go ahead and do this. This capacitor is actually bigger than the capacitors in the camera batteries, or the cameras. Remember, we're doing, the micro is 10 to the negative 6. About how much? 5.4 joules? Is that right?
I get it.
5.4 joules? 100 times 10 to the negative 6 times 330 times 330 times 0.5?
Yeah.
Oh, simply getting a different number? So this is just 100, or sorry, times 100 e negative 6 times 330 times 330, and that gave you 5.4 joules. So how much is a joule? We always talked about how much a joule is. A joule is the energy that it takes to raise 1 kilogram 10 centimeters. Does that make sense? So a joule, Pete, remember MGH?
Yeah.
So if you had 1 kilogram and you raised it 0.1 meters in a gravitational field of 10, that's how much energy it would take to raise a kilogram, 10 centimeters. It's also this. So that's about 4 or 5 joules right there, that amount of energy. So that's how much these things store. Pretty cool. Okay, questions? We have a capacitor simulation tomorrow. All right, now moving on. The analogy for water works very, very well, and this is how we're going to talk about it for the rest of the time. We're going to talk about charges flowing in circuits. Charges flow from high potential to low potential, just like water flows from high height to low height. If you have water and you have a big lake over here and a lake down here, the water will flow from the high lake to the low lake. Okay? Water flows over a waterfall. It flows from high potential to low potential. Charges do the same thing. They flow from high potential to low potential. A generator or a battery is a pump. We can pump water uphill on this side and let it flow downhill on this side. We can pump water uphill on this side, let it flow downhill on this side. Same thing happens here. We can use the battery to pump our charges to 12 volts and allow them to fall back to 0 volts. Pump them up to 12, allow them to fall. A car battery is about 12 volts. When you connect something to a car battery, it's pumping up the charges to 12 volts and allowing them to fall back to 0 volts if there's something in between. This battery pumps charges to 1.5 volts and allows them to fall back to 0. So it's a 1.5 volt battery. So potential is what you need to get the charges to flow, and a generator creates that potential. A resistor, anything that uses current or uses charge, slows charge down just like a windmill slows wind down. Just like the turbines in the dam slow the water down. You take potential energy or kinetic energy and you send it through a turbine that extracts a little bit of that energy out, so the water has less energy and we can send that energy on. That's how a resistor works. If this is a light or a motor or a diode or a speaker or anything else that uses electricity, what happens is it takes the 12 volts, and as the 12 volts fall down to 0, that gets in the way and takes advantage of that drop. Like if you put a generator in or a turbine in a waterfall. As the water falls to the turbine, it slows down a little bit as it falls, spinning the turbine. That's what a resistor does. And they also kind of function like the brakes on your car. Do you want to ride your brakes down a hill, like keep your foot on the brake pedal? Why is that a bad idea? Yeah, it wears out because they get hot, exactly. The kinetic energy your car has is turned into thermal energy in your brakes. So it gets hot. Similarly, resistors slow down the electrons in the material. That's what they do. They take a little bit of the kinetic energy out of the electrons and turn it into some other form. Just like the brakes take kinetic energy out of your car. Oh, and closed, if you don't already know this, closed is the word we use for a circuit that is complete, a complete loop. If the loop gets broken, the circuit can't flow anymore. Charges don't spill out like water would, but a circuit that is closed is allowed to move. If it is open, that means incomplete. So closed is the word we use. Okay, more concepts. Voltage, current, and resistance. Voltage is a quick term for potential difference. Okay, voltage is a quick term for potential difference. Now, if you wanted to know the difference in height of a waterfall, you look at the top of the waterfall and the bottom of the waterfall. You say, well, the top of the waterfall is at 10 meters, and the bottom of the waterfall is at 0 meters. So what's the potential difference of the waterfall? 10 meters. Okay? And the pump, the top of the pump is at 10 volts, the bottom is at 0 volts, so what's the potential difference of the pump? Get the idea? That's how it works. So if maybe it's 10 and 4, you have a potential difference of 6. Okay? So when you measure the potential difference, you measure above and below, or before and after a device. And that'll be important when we actually do the simulation to build circuits. We're going to build circuits. Current. Current is the rate of charge flow. If you wanted to know how much water was traveling through the river or through the waterfall, you'd have to put something in the waterfall itself or in the river. To measure flow rate, there's usually this little stick with a boat propeller in the back. You stick it in the river, it spins around. That tells you the flow rate. You actually put something into the river or into the waterfall. Similarly, if you want to measure current, we have to put a flow meter into the circuit. This is called an ammeter. It measures amps. It measures current meter. Okay, how are we doing so far? Give me a thumbs up if you're with me conceptually. Okay, we're getting there. Some of us are good. Okay, any questions? So we are going to do some simulations on this over the next couple days. But, all right, cool. You know what? I do not want to talk about this. Talk about this later. Voltage. Now, variables and units. Voltage is nice because both the variable and the unit is V. Unfortunately, the same as volume, but both the variable and the unit for potential difference is V. The variable V, standing for potential, gets the unit V, standing for volts, named after Alessandro Volta. That's voltage. Current is named after another guy. Current gets the variable I, but the unit A, standing for amperes or amps. So in your car, you have lots of fuses, and they're all rated in amperes. 30A, 20A, 15A, 40A, 10A, 5A. they're designed to blow when you exceed the 5A. So if you try to put a whole bunch of stuff into your cigarette lighter with a whole bunch of dongles all separating out, like I got 5 things plugged in, you're probably going to blow your 5 amp fuse in your car because they're only designed for 5 amps. It's current. When you blow a fuse, which is actually a breaker, when you blow a fuse in your garage because you tried to cook toast, use your microwave and coaster oven and grill all at the same time, that's because you were drawing too many amps, too much current through the house. And the wires are like, hey, we're only rated for 30 amps. You try to pull 40, we're going to melt. Now, current is a rate of charge flow. The unit we use for charge is the coulomb. The unit we use for time is the second. 1 ampere is the rate of 1 coulomb passing a point in 1 second. 1 coulomb in 1 second is 1 ampere. It's a lot. Just to give you an idea, you only need about 1/100 of an ampere to stop your heart, for your heart. Put it for your hand, you could take a couple amperes without actually burning yourself. Still, it would hurt. Power. Power is still the rate of energy use. It's still a joule per second. It's still a watt. This is the exact same unit we used when we were lifting the heavy weights. Remember with the power pulleys? We're lifting the heavy weights up? The same unit, power is joule divided by second. It's the same watt. So we can rate a motor in watts. We can rate you in watts. We can rate a puppy dog in watts. It's still power divided by time. Now power has 2 formulas, P equals IV and I squared R. And why it has 2 formulas, you'll see on the next slide. P equals IV and P equals I squared R. I wish I could impress on you just how eloquent all these formulas are, how beautiful they all fit together, because they all interact with each other. Power, energy, resistance, current. Question?
What current formula should we write?
The current formula? Oh, Q over T. Yeah. Charge divided by time. Charge is going to be coulomb, just like before. The unit, the variable Q has a unit coulomb. You know, I really wish they had a different C for coulomb and capacitance, but they never asked me. Okay. Other questions about this? All right. Last thing to talk about is Ohm's law. Some people will tell you this is Ohm's law, V equals IR. We're going to use V equals IR a lot. Pretty much for the rest of the school year, we're going to be using V equals IR. We're going to be using it a lot. And people will say, that is Ohm's law. Well, that is Ohm's law as much as F equals ma is Newton's second law. Newton never wrote down F equals ma. Similarly, Ohm's law is not really V equals IR, that's just a great formula. What Ohm's law really states is something that obeys Ohm's law has the same resistance regardless of what voltage you apply to it. In other words, this screwdriver will probably be ohmic if I apply 1 volt to it, 10 volts to it, 1,000 volts to it. But if I try to apply 100,000 volts to this, it's not going to be ohmic anymore. It's going to undergo some crazy changes. Was that hot dog ohmic? No. When it encountered voltage, it had a radical change. So when we're talking about Ohm's law, what we really mean is a material that obeys Ohm's law, or is called ohmic, is a material that doesn't undergo a change when you apply voltage to it. It has the same material constants, it has the same resistance, the same conductivity if you apply 1 volt to it as if you apply 100 volts to it. So again, we tend to say V equals IR is Ohm's law, and that is a critically important formula. But what Ohm's law really is something that obeys Ohm's law, doesn't change its resistance depending upon what voltage you apply to it. There's 3 orders. did it with period 4, but we're not going to have any time to do it today. Okay, so thank goodness the variable for resistance is R. Yes, finally a variable that is the same thing as its name. The variable is R. And the unit is a Greek letter. The unit is the omega. Let me show you how to draw an omega. To draw an omega, you make a flat line, and then an O and another flat line. So flat line, O, and another flat line. So that's to make an omega. Make a flat line, then an O, and another flat line. That's an omega. That is the unit for resistance. As a certain student said last period, it's like the inside of a horseshoe. Okay. So conductors generally have a very high, a very low resistance. Insulators have a very high resistance. Your resistance is about 500,000 ohms from thumb to thumb, about 500,000 ohms, in case you were wondering. Okay. Questions? Okay, we're going to end there because I want to move on to the next thing.